Let's continue with our discussion about linear separability from the last video. We'd established that each neuron corresponds to a straight line on a graph of two inputs, which separates ones from zeros, and that the chosen weights can establish the gradient and intercept of the line. It won't surprise you to realize that for 3 inputs our line becomes a two-dimensional plane, and although we can't draw it, this extends to be an n-1 dimensional hyperplane for n inputs. We also found that we can combine lines together using further neurons in the next layer. And in fact, we can enclose areas by using this idea to separate one enclosed pattern for another, as shown on the screen. So, in fact, we can separate any number of patterns like this, providing that we have one output neuron for each pattern, and that we make the output of this neuron a 1 when that pattern is present, and the other neurons zeros. This means that we only need this type of network, providing that we stick to the rules. This also explains the output coding which was first mentioned in video 18. Note, however, that if we wanted to take this a stage further, we could combine these patterns together using one further layer into any mapping we desired. So in theory, a 3-layer network like this could produce anything that we wanted. This is shown on the screen. This is why simple shallow networks of this type never exceed 3 layers. But as we will see later, networks with more layers have other advantages and are known as deep neural networks. In the next video, we'll consider how many neurons there should be in each layer for more complex patterns.